Okay, cool, thanks. So I'm doing the preview of the probabilistic inference session, and as you will see, we all took very different approaches to preparing the session previews. So I decided that I was going to try to bring across why probabilistic inference is hard and why there's so many papers on this topic. And in order to bring this across and to sort of wake up the audience, let's play a game. So there's this classic problem called the Monty Hall problem, which is about a TV show where every week there are 3 doors, and behind those 3 doors there are 2 goats and a Mini Cooper. And if you choose the right door, you get the Mini Cooper. And maybe the car changes every week, so you can get a better car. And so the way the game works is that in the beginning, you, the contestant, can choose a door. So let's say that I choose door 1. And then Monty, who is the talk host, he will open one door for you that has a goat. So let's say that he opens door 2, and door 2 has a goat. And at that point, you are given a choice. You can either keep your door, the door you chose, or you can switch to door 3. Who would like to keep their door? And who would like to switch? What is better? Is it always better to switch? Or is it always better to keep your door? So who thinks it's always better to keep your door?
I just like goats.
You like goats. Okay, you want the goat. Okay, so the answer is that you should always switch. If you switch, you have a higher probability of getting a car. And what is that probability? I will show it to you in a second, but if you switch, the probability will be 2/3. So in the beginning, I mean, you have 3 doors, one of them has a car, so you have a 1/3 chance of getting this car when you make your first pick. And somehow, once Monty opens the other door with the goat, your belief about what door 3 has changes. So the goal of probabilistic inference, and then I will talk a little bit about probabilistic languages and how we use that to model this sort of situations, is to give you a means to calculate these probabilities so that you can make decisions, informed decisions, as you see new data. So why is it that in this case, you should always switch? I don't know if you can see this. The room is very deep. But basically, in the beginning, when you're choosing your first door, you have a probability 1/3 of getting either the first goat, goat A, or goat B, or the car. Then the host will always reveal a goat. So if you have chosen, goat A, then the host always reveals goat B with probability 1, and vice versa. If you chose goat B, he reveals goat A. If you have happened to have chosen the car, then the host has a 50% chance of showing you goat A or goat B. And if you add up what happens whether you stay with your choice or you switch, you can see that if you switch, there's 2 situations in which you will get a car, and 1 situation you will get a goat. So you actually, if you switch, the only problem if you switch is if you have happened to have chosen the car. But that has a lower probability than you haven't chosen the goat to begin with. And so the probability of winning if you switch is 2/3. Okay? Now, probabilistic programming languages can give you a way to sort of model this situation. And the idea is you have a model. In this case, it's sort of a 3-sided die flip of where you put you have 3 doors. You choose a door at random where to put the car. The other 2 doors have goats. Then you also pick a door at random. And then Monty, the host, will reveal a door that is not the one you picked and is not the one that has the car. And at the end, in the situation I showed you, you observed that you had picked door number 1, and the host had revealed door number 2 that had a goat. And what you want to do when you have such a program is to basically infer what is the probability of your input distribution. And in this particular case, you can actually calculate, as I showed you with that tree, that decision tree, you can calculate the probability exact. You can use Bayes' law, and calculate the probability. You can also do that using something called rejection sampling, And there are different ways of calculating, but you can do it exact. And so the goal of a probabilistic programming language is to give you a way to describe these probabilistic models. And the goal is to have a language that has this inference algorithm that backwards can give you information about your inputs. So how does probabilistic programming differ from conventional programming? In conventional programming, you have some input x, and you have an algorithm described as a function f, and you want to compute an output y. This is sort of the goal of, they say, a deterministic sequential program. In probabilistic programs, typically you're observing something in the output. Like I was observing that, Monty showed me door 2 and I had chosen door 1. And you have a function, f, that that has some random choice in it, and you want to compute the probability on the input x. And this is slightly different from deep learning, which will show up also partly in this session, which is in deep learning, you have the input x, and you have your output y, and you're trying to guess the function, okay? So these are sort of three different aspects of looking at probabilistic versus conventional programming. Now, the function I showed you, written in a sort of toy language to model the Monty Hall problem, is simple to analyze in some sense because the model we're looking at is a discrete model. You have an exact probability and you have a complete description of your outcomes. Things can get pretty hard. You can start having things like sampling from a normal distribution or from a more complex process. And then you might want to infer things that happened inside the loop that uses these parameters. And inference for general purpose languages is hard. You are trying to do this backwards reasoning in a language that enables you to talk about continuous distributions. And this is really hard. So it's very hard to implement a backend that does general inference. And a lot of the work that we've seen in the PL community in the last few years has sort of centered around developing expressive languages together with expressive backends inference engines. And it's a compromise, a little bit like what Diane was saying about cheating versus, I forgot what was the other one, sweating. Here you have a similar compromise, right? You can keep your language very constrained, and then you can do fantastic inference engines, or you can let your language go wild, but then you're sort of stuck, okay? And this is sort of where the work has to go into in order to develop these expressive languages that also have good inference properties. And so the three papers in the session sort of touch in different aspects of probabilistic inference. So the first paper is called Affine Monads and Lazy Structures for Bayesian Programming. And the context of this paper, or sort of the starting point, is to observe that a lot of these Bayesian processes are complex. They have an infinite dimension. And they look at something that we know and love, Haskell, and they look at the lazy language, where we do have capabilities to manipulate infinite dimensional objects like streams and such objects. And they show that, in fact, you can make use of those capabilities that we know so well and love in Haskell to model these Bayesian processes. And then they go further and bring new inference algorithms for this lazy language that they developed on top of Haskell. There's some cool stuff with monads. And what I like very much, the semantics of this language is rooted in a structure that was introduced not so long ago called quasi-Borel spaces. So I'm sure whoever is presenting the paper is going to tell you all about this cool stuff. I see him there, he's smiling, hey Hugo. So he's going to tell you all about this cool stuff. Then the second paper in the session is a very long title called Type Preserving Dependence-Aware Guide Generation for Sound Effective Amortized Probabilistic Inference. I have not seen such a descriptive title in a while, but it does say everything the paper does. So, the context in this paper is that when you're doing inference in probabilistic programming languages, you can sort of guide your inference by using information you might have about the data. And you can use deep neural networks that approximate the distribution of your input using what is called a guide program. So it's a program that is helping your inference engine. And so what these authors did was to develop a way to generate guide programs for a very general, abstract probabilistic programming language. And they use a type system to enforce desirable properties, and they use probabilistic dependence graphs to track correlations between variables in your input distribution. And again, I'm sure they will tell you all about the cool techniques they use to do that. And then the last paper in the session is about smoothness analysis of probabilistic programs. And sort of the context is that when you're doing inference, if you know certain properties of your program, your inference is easier. And one very important property is called the program being differentiable or smooth, as in analysis. And what these authors did was develop a static analysis technique to find fragments of probabilistic programs that are actually differentiable, and then use that to improve the inference process. And so please come to this session. It's going to be very cool. And that's it for today. Thank you.